Hello Internet. This is a drill press that I converted to a mill. I did this a couple of years ago and it's got plenty of use. Most recently I used it on the lathe motor project to cut the aluminum housing for the belt. I can't take off a lot with this. If the cutter binds in any way, shape, or form, it bends the spindle. And then I have to pull it apart and go straighten it on my press. So I've learned to take really light passes. So recently, I bent it enough that I don't think I'm going to be able to straighten it. It's got about 3 millimeters of wobble side to side. And so I need something to replace this. This is a Walker Turner 900 series drill press. This one is a 944. I got it as you see it on eBay for $130 plus shipping. What I want to do is clean this up, convert it to a mill, and replace my old drill press. So if you're interested in that, stay tuned. We'll get started. So I really like this sort of rusty green patina it has. I'm not going to paint it or do anything with the main casting, but I do want to clean up this heavy rust on the handles and on the hardware. So I think I'm just going to remove those, take them out to the wire brush on my bench grinder, and clean them up, make them look kind of like this column. That drill press did not come with a column or a base, so I found this mount. It's from a Delta, I think, or a Delta Rockwell maybe drill press. It's the right size diameter, and it's got a notch on the back side of it, which is really nice. I think this is designed for mounting those drill presses to a metal table, and I'm going to use it for something similar. I'm going to install it backwards though. So I think I'm going to set it up against the edge of this metal plate. I'm going to drill some holes in it and tap those, and I'm going to mount this to this metal plate with some socket cap screws. One thing I know about myself, I cannot drill a straight hole by hand with a drill. So I'm going to use the magnetic drill press to drill these holes. I want this to be centered on the steel plate, so I've drawn a line at the center line there, and then it's pretty easy. Line up the flat with the back. And I've got a center cut in here to allow for it to squeeze together when these bolts are clamped. So I'm just going to put it there, drop a nut down in these so I've got a good center, and punch all 4 holes with what was once a broken nail set. When it's got good surface contact, the electromagnet on this thing is just unbelievably strong. So that's awesome because it holds the thing stable. So I am tapping a 3/8 16 hole with a 5/16 inch bit. And I've got an ER20 collet in here that works really well for holding drill bits. I've got the column mounted and bolted into the clamp below. I'm really happy with how that has all come together. So I had originally intended to move the head up and down and use the column lock. But the more I look at this, just the space I've got here, the more I think it would be better to move the work up and down and then use a combination of moving the spindle and moving the work to get things where I need them to be. To move this up and down, I'm thinking I'm going to use a linear screw actuator or a screw jack. So this is that Duff Norton screw jack. I've got it setting in this column because it's long. So it has, I think this is a 3/4 inch lead screw, and it measures 18 inches long So it gives me 18 inches of travel, and this thing's rated for 2 ton. So it's vastly overkill for what I'm doing with it. I'm gonna mount this, I think, under the table, centered, and make a plate that'll set and push up on the bottom of that drill table. I want to mount that screw actuator on the base here, so I need to cut a hole in the base where that column can fit. Provide the clearance so that I can mount the actuator flat on the base. I want to mount it directly below the center of the table. And the reason for that is, as it moves up and down, I want it to lift on the center of mass of the table so that it's not binding or causing any sort of uneven wear on the column as it moves up and down. So the way I'm going to determine where that center is, I'm going to use the laser culminator from my telescope. If you like telescopes and you haven't seen it, I have like one video on the topic, so I'll put a card up to it above and you can check it out, but don't do it now. I want you to keep watching this video. So I'm going to center this on this hole, and it will shoot a laser down on the base, and I can use that then to determine where the center of the base is. So I turn that on, put it there. That looks good to me. So this dot represents the center of this table. So this is where I want the center of that lead screw to be. Or, more simply, that's where I want to drill my hole. So to cut that, I'm going to use a 2-inch annular cutter in the mag drill. So here's the screw jack. I do not want to drop this thing on myself. So that's going to sit there somewhere like that. So I want to make sure I've got it centered. I'm going to take some measurements with the calipers and scribe around it so I know where it goes. And then I'll punch these 4 holes and we'll drill them and tap them just like we did the column. This is where the slots are on the drill press table. I think I'm going to drill and tap 4 points on this slot. That will let me slide it forward and back and a little bit this way to get it aligned the way I need to. Just put the work table back on. Alright. There is a rectangular casting in the bottom of that table that measures 5 inches by 3 1/4, and I want to put a piece of steel into that recess and then have the jack push on that. So this is some 3/16 steel plate that's left over from my frame repair on the pickup. But I think I can cut that rectangle out of this, and then to actually attach it to the top of the jack, I'm going to use some jam nuts. So you guys are looking at the bottom of the drill press table, looking upward. This is that plate I just cut out. The way this is going to work is that plate is just going to sit up in that recess, and then I'm going to take a nut and I'm going to weld it onto that plate that threads onto the top of this, and that will hold that plate in place. And the nut will keep the shaft from rotating as it moves up and down. So I need to mark where that is so I get it in the right spot. And then I'm going to take this and we'll get it welded on. Now let's run it up and see how it looks. And I don't want to physically bolt that plate to the table, just because if I do something stupid when moving it down, I want it to be able to separate. So my plan to drive this, I'm going to use a VFD. I've got the step pulleys up here, and I figure with the VFD, that'll give me a usable range of somewhere around 40 RPM up to about 5,000, which will be a nice usable range. I've been giving this lots of thought, and I'm thinking I'll put the VFD back here so I have the readout and I can see the RPM, and I can also easily adjust the speed. But those VFDs, they have massive capacitors in them, and if you disconnect the electricity for them, I counted, and mine will keep energized for 30 seconds after it's unplugged. So for 30 seconds it's still got power, and for 10 of those seconds it's still got enough power to turn the motor. So I can't rely simply on an electrical disconnect for safety. So I want the VFD, but I also want to have a safety stop switch. So this is the VFD I'm using. I got this one on Amazon. It was right around $100. I chose this one because it's got a large aluminum heatsink in the back. I've got it wired up temporarily with some Romex, just so I can test everything out. This is not the right way to do this. There are house switches and everything else here, but what I want to do is I want to make sure this thing works before I put it on the mill, before I take the time to build all the brackets and everything else. So I've got that contactor switch that I showed you. This is the $100 VFD, and then this motor is 230 3-phase. This one's a half horse 1725. It is not the motor that's going to go on the mill, but it is of similar spec. I've got the contactor wired into a 220 volt circuit in my shop. From there, the two hot leads are wired into the VFD, and then the 3 leads run out from UVW into the motor. This switch up here, this light switch that looks completely out of place, this is representative of the safety stop switch. So this shorts 2 pins on the top header. Effectively, it shorts one of the pins to ground. So that's all set up. Let's fire it up, let's see if it works. So when I hit this button, the contactor should connect and we should get power. Alright, and we do. Safety switch is off. So what I'm displaying now is RPM. Alright, let's check the emergency stop switch. This seems to work really well. I'm really happy with it. So that's what I'm going to use. I need to cut that box out, that metal box, so I can mount this in it. And I need to make a mounting bracket to support the VFD on the machine. And then we'll run the wires. So let's go back over to the machine. I think we'll start with the VFD. We'll get it mounted. And I've got this plate. It's 6 by 12. 3/16 thick, and I'm thinking maybe I could sandwich it between the motor and the mount and then use it to provide a surface to bolt that VFD to. That would put the VFD right up kind of next to the motor in that area, kind of where I want it, and I think this is thick enough it would give it a pretty solid mount. So I'm going to just scribe these slots here and then figure out where the motor needs to go on here, and then I can drill 4 holes in this and I'll have the bracket for the VFD. So I thought while I'm wiring this up, I'd take a quick second to show you how to wire it. This is a dual voltage motor, 230/460. When you're working with one of these, the low voltage is the 230 side. So these 2 diagrams here show you how to wire it. My motor has a nest of wires in there. And if you look at this, what this is really telling you is L1, L2, L3, those are the motor inputs that come from your VFD. So if you have one of these Chinese VFDs, they're usually labeled UVW. So L1 is U, L2 is V, and L3 is W. So that's where you would connect those. So when you wire this together, you'd have T1 and T7 bound together, T2 and T8, and T3 and T9. And then T4, 5, and 6 are tied together on their own. So now it's time to actually wire this up. I'm going to have the power from the wall come in through a knockout, and then I'm going to wire the emergency shutoff switch in the middle, and then on this far side it will run out to the VFD. So I'm going to do that now. Let's get this wired up, and then I'm going to turn it on and see that motor spin. Alright guys, I got it wired up. So I ran a 220 line and a drop from the ceiling. That runs into the control box here. In this, we've got the contactor and the emergency stop switch, and then that powers the VFD, which powers the motor. So I've got the VFD up, it's wired, I put the belt on, I got the spindle back in. So I'm going to turn it on, I want to show it to you guys. I want to show you how it works, and then there's only a couple more things we have to do, and then we'll be able to actually mill something with this. So power on. Set the speed, we'll slow it down to nothing for the first run here. And I'll just pick a number. Alright, so I'm going to go right in the middle of the RPM range. So this is 771 RPM, and it's in its second slowest gear, or pulley set up top with the belt. I can calculate that out, and I may calculate it out and put it on the screen as to what this RPM is. Let's take it all the way up. So that's at 1728. It's really quiet. I am getting some vibration off of the motor. I've got to figure that out. I don't know, it may or may not be a problem, but this is really cool. And the E-stop switch works. It just cuts power to the motor. So the VFD is still there. To reset it, pop it out, hit the run button again. And anytime I hit it, it'll cut power to the machine. I can also run it in reverse. I don't imagine I would ever use this feature, on this machine anyway, but it'll do it. Here's a little bit better look at the VFD. So the dial sets the speed, but we also have other things we can see. So that's the RPM. That's what amperage it's currently pulling. It's 0.8 amps, 0.9 amps really. The VFD itself has 17 minutes on it. I don't know why that's not particularly useful, but and then the frequency is currently held at 36.5. If I were to hit the stop button, this will go to an F to indicate that that's the set point or the target. So there's really two things left I have to do. One, this collet right now is only being held in place by the taper. It's pretty easy to get off there with a mallet and a punch. I need to secure it physically to the spindle. So what I want to do is modify this collet to include a snap ring and then make a new lock ring so that I can draw it up and lock it into place with this threaded lock ring. That'll keep it from coming off. I won't have to worry about it. So that's one, we have to build the collet. And the other is the hand wheel for moving the table up and down. We'll have to build that. So I'll walk you through how I'm going to do that. So let's start, I think, probably with the hand wheel. I think that's going to be the easier of the two. So I'll show you what I'm going to use for that. So here's what I'm using for a hand wheel. So I got it, I bored it out to a 1/2 inch, and I tapped it so that it would thread onto a 1/2 inch bolt. And then I'm going to use a 1/2 inch nut to lock it in place. So this will be the hand wheel assembly. And then I'm going to cut off or turn off the head, cut a keyway, and I'm going to mount it to the shaft here with a shaft coupler. So we'll end up with something like this. And then because this does stick out so far, when I rotate it, it's going to get a load about it like this. And so to support that, I have this piece of metal that came off of the surface grinder. This one had a rod go through it, and I thought maybe it was for holding like instructions or prints, but I don't know, I'm not putting it back there. But it's just about perfect for this. So the way I think that'll work is I've got the bolt here that'll become part of the screw shaft, and that'll fit in the opening in this steel block. And then the handle will go on, and this will act as a support piece. I'm going to have to modify it a little bit, so it's not quite tall enough, so I'm going to have to add some spacers. And then I also want to bore out this hole for the shaft, and I'm going to press in a bushing. This is the chuck that originally came on this machine. It's a Jacobs 6A chuck. It's simply held in place with a taper. A lot of drill presses in this era had these threaded collars that you could use to help remove the chuck. So when you unscrew that collar, what you're left with is a spindle with a Jacobs taper 33 on the bottom, and then this threaded portion that this collar went onto. So this threaded portion is 1 1/16 inch, 20 threads per inch. Took me a while to figure that out. As part of the mill conversion, I want to use an ER20 collet. So I got this on Amazon. I've seen them on eBay as well. It's an ER20 collet with a Jacobs taper 33 or a JT33 taper. So this, simply fits onto the taper just like your drill chuck. The only problem is there's no way to secure it. So, get a little bit of side loading on this thing and it can come off on you. But that's where this threaded collar comes in. I want to be able to use something like this to hold this ER20 collet in place. When I put this threaded collar back on and I fit the collet, we've got about maybe a 1/4 inch of a gap there. So this works great if you need to remove this collet. Once it's tapped in place, it'll pull it off. But what I want to do, or what I'm thinking is, get up there, if I make a new nut, one that comes down quite a ways onto this collet, like, I don't know, maybe about an inch or an inch and a quarter, that fits over this with thread on, and then I'd cut a groove in here to fit a snap ring, I could have this collet held into a new nut with a snap ring. That would allow it to turn, so I could draw it up and also push it off. And most importantly, it would keep this from coming loose if it gets side loading or other loading on it. So I mentioned earlier that the threads on this collet are 1 1/16 inch in diameter, 20 threads per inch. For not a lot of money, you can actually get a tap in that size. I got this one on eBay. It was under $40. I was going to cut threads on a lathe, on my mini lathe doing this, but it moves so quickly with the change gears to get 20 threads per inch. I did a couple practice runs, it didn't go well. This is 1.5 inch outer diameter with 1/4 wall DOM tubing. So that gives it an inner diameter of just a lick under an inch. So let's switch over to the lathe. We're going to go back to the lathe. I want to cut a length of this down to that 1.5 inch. We'll turn the inside diameter down to 1.02 inches, and then we'll run a tap through it, and then we'll finish by cutting snap ring grooves, and we'll put a snap ring in here. See if this thing goes together and works like I think it will in my head. I'm working on the collet retainer, or the collar, for the ER20 collet, and I don't have a way to cut wrench flats on it. I tore apart my little mill, and it's what I would use. So I'm going to do something really stupid, or it's probably really stupid. I've cleaned up the taper and I've tapped this in place, and I'm going to try milling the flats on it with the new big mill without any sort of retention mechanism. Now this could go south in a hurry. We're cutting steel with a high-speed cutter. This is a 1/4 inch. I'm going to take some really light passes until I kind of figure out how this thing performs, and just to be careful. And this is going to be the very first time this mill has ever cut anything. That's how that came out. Those are the lands for the wrench. That'll give me something to hold on to, or the flats. I think that's okay, especially for really the first thing this machine has ever made. See how that looks. Oh yeah, that looks really nice. I had planned to cut a snap ring groove on this side, and that would engage a snap ring on the collet chuck that would pull it upward. This thing is hardened, and I had a hell of a time cutting into it, so plan B, I'm going to put set screws in, and I cut a line to show me right where the set screws go. This one here is the first one I made, and it turned out really miserable. It's off center, tolerances are really bad. It was the one I figured out what I was doing on. And so on it, I tapped and installed set screws, and that worked really well. So I'm going to do the same thing on this one. So I've marked the location for the set screws. I'm going to hold them in the vise here, and we're going to use the mill to drill them, the new mill to drill them. Alright, now let's see if it spins true. That looks alright to me. What do you guys think? Can you see it? Oh yeah, you can see it. You're looking right at it. Alright. Well, let's mill something. Let's see if it works. Alright, so this is a part of the tool post for the Atlas lathe. I need to machine this into a T-slot that fits in its tool post. I started on it on the old mill press, the little one, but it just really wasn't up to the task. And so I figure we might as well see if we can finish it on this machine. So I'm going to turn this thing on, and what my goal is just to remove material down to this first line, and then once I get to the first line, we'll flip it over, do the same thing on the other side, and then I'll start milling the T. I'm going to run over it and just clean up the mess that was left by the other press. Alright guys, so here's how that part turned out. Everything was going really well, and then it wasn't. I was having good cuts, good smooth finish, and then I started getting chatter, and it got really bad, and it broke the end mill. So I put another one in, and it broke that within a few minutes. And I got really frustrated with it, and I put a third one in, and I just rammed it into the part. So I had to stop, take a step back. This is where the part ended up. It's pretty much ruined. The chatter it took too much out of this face. So I threw it away, but then I dug it back out of the trash to show you all. So I walked away from the machine for a little bit, and when I came back, I started looking at it, and I pulled the spindle out, and it's got absolutely no play in any direction, except it's developed play in the up and down. I don't know if you guys can hear that. But there's about 25 thousandths worth of play up and down. And what I think is happening is that cutter is just hopping on the part, and that's creating the chatter. And once it starts, then it just goes. So I think the solution here is to replace those bearings. I'm going to pull the shaft apart, see what's in here. I don't know what these bearings look like. I did not pull them out, so they're the 80-year-old original bearings. So I'm going to see what's in there, but I'm going to save that for another video. I will admit, I got to walk away from this thing for a while. So despite how this turned out, I had a lot of fun making it. It's a really good tool. I think, I've just got a couple of teething issues here to resolve. So if you've got a drill press and you want a milling machine for just light duty around the shop, this is actually not a bad way to go. People will tell you shouldn't do it, probably for reasons like this, but we don't all have the space for a Bridgeport, or the money, or the electricity, or the know-how. And sometimes you just need to mill a little bit off of a piece of aluminum or whatever. This is really good for that. Don't let my results, hold you back. So I appreciate you all taking the time to watch this. If you found it useful or you enjoyed watching it, would you consider subscribing to my channel? Those subscriptions really help, and I have a small channel. I'm trying to grow it. I like doing this stuff and I want to do more of it. Seeing new subscribers and that interaction, I really enjoy it. So, if you enjoyed it, would you consider subscribing? So keep an eye out. I'm going to release a follow-up video where I replace these bearings and hopefully resolve that chatter. So with that, I'm going to wrap this one up. Thank you for watching.